Okay, so we're going to go ahead and take a look now with at projectiles that are launched at an angle. Okay, so we've been looking at horizontal projectiles, ones where we just shoot them straight out. But the fact is that not all projectiles are shot straight out. So we're going to look at projectiles at an angle, meaning it can be launched up like this at some angle, or down like this at some angle, and we're going to look at how that changes things. And really, it's not too big of a change, but there's one key difference, and the key difference is that with when we're looking at like all the information we have for a horizontal projectile, the initial velocity for y is equal to 0, whereas for a projectile launched at an angle, this is not going to be equal to 0. It'll be equal to the y component of the velocity. Okay, and so this is kind of where the challenge comes in. In order to analyze these, we have to kind of take the information we're given and break it into components and then analyze it from those components. So we're going to start off by analyzing a projectile that we're going to say is launched at 30 degrees above horizontal, we'll say. Okay, so 30 degrees above horizontal has a velocity of 25 meters per second. Okay, and so we're going to analyze this. Let's say it's on a cliff here, and the cliff has a height of 40 meters. Okay, so we're going to analyze this scenario, but before we get too deep into that, I want to take a quick look at just kind of some of the intricacies of projectiles launched at an angle. Okay, and some important things to remember. Okay, so if you look here, some of the things we want to remember are this, and these are kind of the key points that we need to pay attention to when we're analyzing a projectile. So the first thing is we're given this velocity. Okay, this is the magnitude of our velocity, the magnitude of our starting velocity. Okay, and so what we need to pay attention to here, though, is first of all, we can't work with this because this isn't in one dimension, it's in two dimensions. So in order to explore the properties of this projectile, we have to break it into two separate dimensions and analyze them individually. Okay, and so the way we do that is to get the horizontal and vertical components using sine and cosine. Okay, turning it into a triangle and finding its components. Okay, the next thing, and these are just properties of the flight. If you look at this, there's a couple things I want you to notice. First of all, at the peak of its flight, it has a vertical velocity of 0. So like when we analyzed horizontal projectiles, it was as if we started from this point right here. Okay, and this part never happened. Okay, and so before that, we have all this new stuff going on. But what's important here is at this highest point, our vertical component for velocity is equal to 0. Something else that's really important to know is displacement vertically is just how far away from its starting position is. So as we go up, we have positive displacement, as we're coming back down, positive displacement, 0 displacement. At this point of the flight, the vertical displacement is equal to 0. Okay, because it's at the same height that it started. This is really important. The second thing here that's really important is that if this is v naught y, then this is negative v naught y. When it's come back down to its starting height, it has the same vertical speed, but it's going in the opposite direction. Okay, so the direction has flipped. The last thing I want you to remember is acceleration. Always down. Okay, acceleration always down no matter where it is in its flight. Okay, and if you can remember those things, then you should do all right. The other thing to remember, this horizontal velocity never changes. It's constant the whole time. This vector never changes its length. It's always the same length. Whereas you can see this getting smaller to 0, and then increasing the other direction. Okay, and so that's a a projectile launched at an angle. Okay, and then before we get further into analysis, we're going to go back to the original one we had. Okay, and so we're going to analyze this. I'm going to show you basically like an animation of this. So we have a projectile starting at a height of 40 meters. It's launched at an angle of 30 degrees and has a starting velocity of 25 meters per second. Okay. Okay, so I've developed I've kind of took it that earlier simulation we saw. I've made it a little bit more advanced so that we can like make it fit our scenario. So here we have a starting height of 40, initial velocity of 25, launched at an angle of 30 degrees. Okay, we have our acceleration downward of 9.8 meters per second squared. Okay, now we're going to zoom in on this real quick. I want to show you something. Here you can see the magnitude of the velocity, the starting velocity. Here's our starting position, and we have this green vector here represents that vertical component of the velocity, and this represents that horizontal component of the velocity. Okay, and you're going to watch that as it flies through the air, this vertical component is going to shrink, but this should stay the same. This is going to shrink, and then it's going to turn around and increase the other way. Okay, so also you can see that it's going to calculate the initial quantities for each. So in this case, the initial velocity for y is 12.5 meters per second. We get that by multiplying sine of the angle times velocity. This calculator only does sine in radians, so I had to convert it to radians. And then same thing here, we get the horizontal velocity for x. So this is 21.7 meters per second for x, 12.5 meters per second for y, and then we'll go ahead and watch the simulation real quick, and we'll highlight some things as we watch. Okay, so we're going to go ahead and play it. Alright, and there you can see it, the projectile flying. Okay, and so a couple things I want you to notice as it goes. Okay, so first of all, hopefully you noticed that this piece right here had a velocity that changed, so it was starting upward and then it's starting to increase its velocity downward. Hopefully you're noticing that this piece right here is staying the same length the whole time. Okay, and this is kind of what it looks like. Okay, we can even take this and make a guess about how long it's going to take to hit the ground. So if I take and adjust this time slider, we're going to see that it looks like it's going to hit the ground after about 4.4 seconds, and at that point it looks like the horizontal displacement is going to be about 95.2 meters. Okay, and so those are things that we're going to actually go ahead and calculate, and we can kind of see. Okay, but let's just kind of step through this again. So pay close attention as we step through this to the vertical velocity. See it shrinking. At this point it's at the highest point, so it's 0, and then it increases the other way. Okay, and also pay close attention to that horizontal vector for velocity. Okay, it's the same the whole time. It doesn't change. It moves at constant speed horizontally. Okay, so anyway, I will share this with you so that you can also make predictions with this. So like if you're working on a homework problem, you want to test it out, you can make predictions. You can also launch a projectile at an angle that is less than 0. So like if you can launch a projectile downward at an angle. Okay, and so what changes here is you can see that if it's launched at an angle downward, then the initial velocity here is going to start off going down. Okay, and so one way you can think of the angle is it kind of tells you if we have kind of this like, let's say that we have this kind of like parent function for projectile motion. Looks something like this, maybe just a inverted parabola. And so changing the angle is going to kind of change whatever your starting position is. So let's say if you start with an angle downward, that means you're going to start somewhere over here. If it's a horizontal projectile, with meaning the angle is 0, that means you're going to start right here. And then if you have an angle going up, that means you're starting somewhere between here and here. And that's one way you can kind of think of it, okay? And then if the angle is 90 degrees up or down, then it's just an object it's not a projectile anymore, it's just a falling object, okay? Okay, so we're going to analyze this scenario where we have this projectile launched at an angle, okay? And always the first step is going to be to find our components for velocity. So our initial velocity for y and our velocity for x. Remember, this doesn't change. This is the starting value for y. And so the way that we can find that is we're going to take this and use the trig to break it into components. I'll find the horizontal component, you can find the y component. So Vx is going to be equal to this horizontal piece here. Vy will be this vertical piece here. Okay, so Vx equal to V times cos theta. Okay, so Vx equal to 25 meters per second times cosine of that angle of 30 degrees. Okay, and that's going to give us a velocity of about 21.7 meters per second. Okay, so Vx equals 21.7 meters per second. So I'd like you to go ahead and find V naught y. Okay, so V is 25, angle is 30, we get 12.5 meters per second. Now we need to make a decision about which direction is positive, okay? You can always choose up or down. I'm going to choose up to be positive in this example. Okay, so that means we start with a positive velocity of 12.5 meters per second for our initial velocity. We know that our acceleration is downward, negative 9.8 meters per second squared. Okay, and then we can kind of look at two things. We can look at when it hits the ground, okay, in which case our displacement for y there would be 40 meters below where we started, or negative 40 meters. And then we can also look at when it gets to its highest point, in which case our velocity there would be equal to 0 meters per second. Now those are two separate scenarios, and those are two separate pieces of information, and so we can't use these together, but these represent two different snapshots, okay? If this is our projectile, okay, at this point v is equal to 0. At this point, delta y equal to negative 40 meters. Okay, so the first thing that we're going to find is, maybe let's say, how much time does it take to hit the ground? Okay, which means that this piece right here isn't valid, because that's talking about up here. Looking at this scenario, we're looking for time there. Okay, so if you have these three quantities and you want to find time, which equation would you like to use? Okay, so to find time, we could either use this equation right here. The problem with this is we're going to end up with a quadratic that we have to solve, or we could use this equation right here to find final velocity, and then once we find that final velocity, we can solve for time. Both of these will work. It's totally up to you which way you want to go. I'm going to say use this one if you have like a quadratic solver you could use, and if you want to save yourself some time, use these two. Okay, so either way, our initial velocity for y is 12.5 meters per second, acceleration negative 9.8 meters per second squared, displacement negative 40 meters. So using that info, go ahead and find how much time it's going to take to hit the ground. Okay, so I went ahead and went this route right here. I used this equation to solve for the velocity. I got negative 30.7 because it's downward. I put it into this equation here and found that time was equal to 4.4 seconds. Okay, now we're going to go ahead and do another one, or now we're going to go ahead and find the maximum height. The height, it is right here. So now this information here is valid, but this information is not. Okay, so you have 1, 2, 3 pieces of information. This time also not valid for finding the highest point here. So you just use these 3 pieces of information there. Go ahead and try to solve for it. To quickly wrap it up, to find the highest point, I used this equation right here. I said the final velocity was 0 for that highest point, and I got a vertical displacement of 8 meters.